This is part 2 of the DAQ lab. This video covers the electrical engineering experiment using a thermistor. To review, the objective of the DAQ experiments is to illustrate manual data acquisition. You will collect raw data, set up a spreadsheet, perform calculations, plot the data, calculate trend lines, assess the goodness of fit of that trend line to the experimental data, and assess the experimental error between your experimental measurement and the manufacturer's data sheet for the thermistor. First, an introduction to thermistors. The word thermistor is a combination of thermal and resistor. A thermistor is a passive element used in electrical circuits. It is a resistor, but the value of its resistance is temperature dependent. The circuit symbol for the thermistor is provided below. In this experiment, we'll be using a negative temperature coefficient, or NTC, thermistor, which experiences a decrease in resistance as temperature increases. An image of the thermoresistor that will be used in this lab is provided below. As you can see, it's quite small. The relationship between resistance and temperature is not linear. This figure indicates that the shape of the curve is similar to that of an exponential decay curve. The governing equation for the behavior of a thermistor is a variant of the Steinhart-Hart equation. R is the resistance in ohms. R naught is the nominal resistance at T naught, also in ohms. T is the temperature in Kelvin. T naught is the nominal temperature in Kelvin. And beta is the sensitivity of the thermistor. Another electrical device that we will be using in this experiment is a thermocouple. Thermocouples are manufactured from wires of two different metals that are welded together at one end to form a very small bead. In the figure shown, this bead is inside the pink square labeled T sub sense. At the other end, they are wired into a device that measures the voltage differential and converts that voltage to a temperature. Let's look at the experimental setup for experiment 2. To conduct this experiment, the required materials include a digital thermometer, a K-type thermocouple, a digital multimeter, multimeter leads, a desk lamp, a stopwatch, a small block of wood, a zip tie, and the test specimen. You will need to provide a piece of paper and a pen or pencil so that you can collect the data from the experiment. Now let's look at the test apparatus. The purpose of the wood block is to provide firm attachment of all the components together. This slide contains 3 images of the wood block with the components attached to it. The image at upper left is the front face of the block. The image at bottom center is a close-up of the first image. The image at upper right is the back face of the block. 5 small holes were drilled through the block of wood, 3 in the center and 2 close to one edge. From the front face of the wood block, the thermocouple with blue insulation was passed through the leftmost of the center holes. The silver bead that the blue arrow is pointing at is the point at which the 2 wires of different metals were welded together. The 2 leads from the thermistor, which is the black bead, were passed through the center and the rightmost holes. The thermistor and the thermocouple were mounted in close proximity to each other so that the experimental measurements would be made at the same temperature. On the back face of the wood block, the red and black multimeter leads were connected to the thermistor leads. A zip tie was passed through the two holes near the edge of the wood block and was used to stabilize the three leads so that they wouldn't become disconnected in the middle of the experiment. In this slide, you're shown the two parts of the test apparatus. In the photo on the left are the three instruments that will be used to take the experimental measurements. The thermocouple lead was connected to the digital thermometer. When the thermometer is turned on, I will verify that the temperature is measured in degrees C and that a type K thermocouple was selected. The black multimeter lead was plugged into the center port, which is the common ground port labeled COM, and the red lead was plugged into the right port, which is labeled for the measurement of voltage and resistance. To turn on the multimeter, the switch is turned from the off setting to the position labeled with the Greek letter omega, which is the symbol for ohms, the units of resistance. And finally, I'll be using the stopwatch on my cell phone to measure time. The thermistor and thermocouple on the wooden block were placed under the desk lamp, and the lamp was adjusted so that the bulb was placed close to the thermistor and the thermocouple. You will take the first set of measurements before the lamp is turned on and the stopwatch is activated. Before you start the video for the experiment, you need to prepare your data collection sheet. You will collect 3 columns of data: time, temperature, and thermistor. Write both the variable name and its units in the column heading. This will prevent confusion later on when you're working on your data analysis. Your form may be computer generated as shown here, or it can be completely handwritten. I've provided a copy of my blank form here as an example. Because the data is nonlinear, the thermistor's resistance is going to change rapidly at the very beginning of the experiment. So my suggestion to you is that you will pause the video at the beginning at 5-second intervals for the first 15 or 30 seconds until that change in thermal resistance starts to slow down. After that, you can select a longer interval of time, perhaps 10 or even 15 seconds between each data point. Following is the video of the 3 measurement devices taken just before the lamp is switched on, so that you can collect the data at the start of the experiment. You'll see my hand come into view. I will start the stopwatch when I turn the desk lamp on. Begin the video when you are ready.